Perfect.
Okay, so today I'll talk about some efficient penalized regression methods, and especially I will give some example from my work, so about genetic prediction. So first I'll start with a bit of context. So you may have heard of the term polygenic scores. So polygenic scores are like a score that combine many genetic variants into a predictive score that can predict things like height or for example disease risk, like the probability of being diagnosed with heart lifetime. So when it's specifically talking about disease risk, then we can call it polygenic risk score, but it's basically the same thing. And one of the main benefits of polygenic score is that the genetic variants don't really change over time. So basically, you could get this score as early as birth, and then so you could get, like, from age 0, you could get your risk of being diagnosed with heart disease during lifetime. So it would be really useful in case of prevention, for example. And I will give some example later. But one thing that is very hard about deriving some polygenic score that are predicting very well is that most traits or diseases are what we call very polygenic, meaning that there are many variants that are associated with the disease, meaning that they have non-zero effects, and usually these effects are very small. And we know that in the case of prediction, if you have many variables with like small effects, it's very difficult to predict. So it's one of the main problem but now, because we have large sample size, then we can predict something that is quite good for some traits. And I want to recall that a polygenic score will be limited by the heritability. So the heritability is the proportion of variants that can be explained by genetics. So if you have a trait that, for example, height, that is very heritable, then you can predict a lot from genetics. But then if you have a trait that is not heritable, or I don't know, like 10%, then you can't predict much. So you have to remember that you can't predict everything with genetics. It has to be an heritable trait. And I just want to give an example, like this nice study by Michael and Louis. So and some colleagues, they looked at some genetic risk score for coronary artery disease, and they compare predictive performance of some conventional risk factor like smoking, BMI, and so on, and I compare it to like their method called meta-GRS, so it's a polygenic score for coronary artery disease, and actually this score is better than, is more predictive than any of the conventional risk factor alone. But then when you get them all together, then you get a better predictor. But on top of that, if you also include this genetic risk score, then you get an even better predictor. So basically, it's just saying that the polygenic risk score could be used on top of the conventional risk factor to help the prediction and to help like prevention in clinical settings, for example. And we can see that on the right, sorry. When we look at the cumulative risk of the disease, then the median, for the median population, it would be like you have like a risk of 15% at age, let's say 70. But then if you are in the if you have a high PRS, like if you are in the 20% with the highest PRS, then the risk is like double. So for these people with high risk of getting coronary artery disease, then you could get some intervention or prevention sooner in life, like at age, I don't know, 50 instead of 60, for example. So it can really be useful for in clinical settings. And I will just give now 2 examples from my work. So IT is a very heritable trait, like it's up to 80% heritable. And here with some polygenic, some penalized linear regression, I can predict 40% of variance using genetics only. So half of the heritability I can predict with genetic variance. But okay, see, this is based on a very large data sets. So this is the UK Biobank. So I'm using here 400,000 people. And for all of them, I have like almost 600,000 genetic variants. So in the end, I have a matrix that is 400,000 times 600,000, which is like very, very large. And I will show you how is it possible to train a penalized regression on this kind of data. So another example from my work. So this is based on a smaller data set of only 15,000 people, but it's still 15,000 times like 500,000. So it's still very, very large. So celiac disease is like gluten intolerance, and it's an autoimmune disease. So basically, I said before that most traits, like height, for example, are very polygenic, meaning that they have many variants associated with the disease, and each of them has very small effects. In the case of autoimmune disease, you can have large effects on chromosome 6 in a region that encode for like some autoimmune system. So in this case, you don't need a very large sample size to get a good prediction. So here I can get up, so PLR is like a penalized logistic regression. I can get up to 89% in terms of area under the rock curve, which is a very good predictor. And yeah. So just this was just to give you some context and some example to get you excited about this work. And now I will just make a quick reminder about penalized regression models. So in linear regression, standard linear regression, for example, if you have a continuous phenotype, then you want to solve this model where you have like an intercept and then all the genetic variants, and then also some other covariates. For example, you can have sex, age, or we use also some principal components to account for population structure. So there can be like many variables, like hundreds of thousands. So if here I just use a more compact terminology, like with vector beta and a matrix X, I can just write it like this. And then we just want to minimize the sum of quad errors. And then we know that there is an analytical solution for this problem, which is this one. But so the question is, what is the problem of this when you analyze, for example, genotype data? So the thing is that usually the sample size that I call n here is usually smaller than the p, the number of variables. So as I said before, you have like hundreds of thousands of genetic variants, but maybe only tens of thousands of individuals. So this makes this X transpose X not invertible. So you basically the linear regression doesn't have any unique solution. So one way to solve this problem and still use linear regression is to use penalization. So for example, you can use the L2 with the regularization with the L2 norm, where you just add this lambda times the square norm 2 of the effect size. And this still has an analytical solution, which just corresponds to adding this lambda value to the diagonal of x transpose x. And then if the lambda is large enough, then this makes x transpose x plus this invertible, and then you can have a unique solution. And so this L2 regularization is called rich. And basically it shrinks coefficients towards 0. So it makes them a bit smaller, or sometimes a lot smaller if lambda is large. You can also have like the L1 regularization, which is like with the norm 1. And then this doesn't have any analytical solution, but there are some iterative algorithms that work well to find a solution for this. So the solution is like finding the beta that minimizes this. And so this is called the lasso. And so that this L1 regularization, it forces some of the coefficients, some of the betas to be exactly 0. So it's people usually like lasso because then you don't have all the variables that enter the model. So it can be useful, for example, because it makes the model more interpretable. And what you can have also is a combination of both regularization, the L1 and L2, with like a convex combination of these two norms, like with the alpha. So between this alpha would be between 0 and 1. With the special case when alpha equals 1, then you end up with the lasso, and then if alpha equals 0, then you end up with the ridge regression. And in between, it would be called the elastic net regularization. And it's a compromise between the two, and usually it has the benefits of both and without the limitations. So it's quite good. So usually people also very like the elastic net regularization. And just to talk a bit about the advantage and drawbacks of penalization. So the advantage, as I said, first it makes the problem solvable. If you have more variables than individuals, like sample size, and don't use penalization, then you don't have any solution, so you can't really do that. And also it generally prevents from overfitting, meaning the generalization in another dataset is better than when using like standard linear regression. So it's usually very good to use this penalization, but the one problem I would say is like now you have like two hyperparameters. So you have one hyperparameter, this lambda, that controls the amount of penalization that you have in your model. And if you use elastic net regularization, then you have also this alpha, which is the relative contribution of the two norms. So if you use elastic net regularization, then you have two hyperparameters in the model that needs to be chosen. And usually, so it's usually done by grid search and cross-validation. So yeah, I will talk about that just later. An alternative that I've seen in some work, for example, in genetic data, is to do what we call a GWAS, a genome-wide association study, where you take each genetic variant independently and look at the association with the phenotype. And so you get a p-value from testing if the effect of this variant is different from 0. And what you can do is like keep only a subset of variants, like the subset with the most significant variants, so with the smaller p-values. And then if you take a subset that is small enough, then you can fit a standard linear regression. And a heuristic is like having a sample size that is 10 times as like the number of variables to estimate well the effect size. But usually what I've seen is that using penalized method is usually giving better prediction that using this kind of approach where you just filter before and then do some normal linear regression. And as I said, because you have like this hyperparameters, then you usually use cross-validation. So just from in cross-validation, you usually split your training tests into, like, for example, 10 folds. And in turn, you use 9 of them for training and 1 of them for validation. So you get the prediction, the prediction that you get with the 9 folds, you evaluate in the remaining fold, and then you do that 10 times and just average. And so you get an error for every set of hyperparameters. And then you choose the set of hyperparameters that minimize the error or maximize the predictive ability. And usually what it's done is once you have like the hyperparameters, the best performing set of hyperparameters, you use them again to refit the model in the entire training set, meaning in the 10 in the 10 folds. So you have to refit the model afterwards. So what I want to say is that, like, for example, in R, there are some there is the package LMNet that is really nice. There are many options. It's quite fast. But when you start to work with large data, like in genetics, and also if you need to do like this cross validation, so if you need to do 10 fit 10 models for each of the each set of hyperparameters, then it can start to be a lot of model with large data, and then it can take like days or weeks. So it's not really possible anymore. So I will show you a slightly different approach that I'm using in my package BigStatRA that solves this problem of running time for large data sets. So I'm using something that is quite similar as cross-validation, but it's not exactly cross-validation. Okay, so first, so imagine you have your data. So you have some test data that independent test data that you don't look at until the end, where you just evaluate the model at the end, and you have your training data where that you divide in say 10 folds, and then use 9 for training and 1 for validation in turn. So how does that work to fit a lasso or elastic net penalized regression? So usually how does like the algorithm work? So usually you start with a lambda that is very high. It's so high that there are no variables that enter the model, so it's only the intercepts basically. And then you start to decrease the lambda, and then there are some variables that start to enter the model because they're just high enough, like the effect size are high enough to go over the regularization. And so you start to fit the training data, and then when lambda is too low, then you start to overfit, meaning that the loss, meaning the error that you make in the training set continue to be to decrease towards zero, right? But if you evaluate your model in the validation set, so a set that is not used for training, then you will see that the model start to be worse, because then you have too many variables that enter the model, and maybe some of them are just noise, and then the prediction is starting to get bad. So you want to stop. You want to choose the model that minimizes the error in the validation set. And also you want to stop because the error in the validations, it's just getting worse. So you don't really have to explore this this model on the left. And it's very important for large data because so as I said, you start with the high regularization with like no variable. You start to decrease the regularization, and then this lambda, and then you get more and more variables. So at the on the left, there are like many variables. So basically the models on the left can take as much time as all the ones before. So what I want to say is that the models are more costly to fit, and so you want to stop as early as possible to prevent you from exploring this costly model. So basically, it's what I do. I use this early stopping criterion. I choose this model that minimizes the loss in the validation set. And so I do that in turn for each of the 10 validation sets. So basically at the end, I get 10 models. And instead of fitting again the model on the entire training set, meaning the 10 folds, what I do is I just average the 10 models. So it prevents me from having to refit everything again. Yeah, so at the end, the model in big stat R. So the function that are available in this package for fitting penalized regression, they will give you an automatic choice for parameters, hyperparameters lambda and alpha if you're using your elastic net regularization. It's also very fast because mainly because of this early stopping criterion. So for some cases, using this early stopping criterion or not using it can be like a tenfold difference in coefficient time. So it's very important in large data sets to use this early stopping. And also because of this cross-model selection and averaging, I don't need to refit the whole data, so I save some computation time here as well. And also in the package, so all the functions of this package use matrix format, but matrix format that is stored on disk, and it accesses the data that only the data that is needed, so only a subset of the data into memory at the same time. So it's quite memory efficient, and also because this data is on disk, then it makes parallelization of algorithms very easy to do. So most functions in this package are parallelized, and here for the penalized regression, what I parallelize is the fitting of the models. So for example, if you have 10 folds and then 5 different values for alpha that you want to try, then it's like 50 models. So these 50 models, you can fit them in parallel if you have enough enough cores, for example. Yeah, so it makes penalized regression and other algorithms or functions. They can be applied to very huge data. And also, very recently, I've added some 2 new options. One option for scaling. So the default is to scale your variables to all have, for example, unit 1, meaning a norm 1. But maybe in some applications, it makes sense to not do any scaling because the data is already on some scale that makes sense. So I've added this option for scaling, and also another option for adaptive lasso, which means that larger marginal effects are just penalized less. It has been proven that it's useful in some cases. And the thing with these new options is that you can provide vectors of value that you want to try the same way as the alpha hyperparameter. So it's just another hyperparameter, and that will be automatically chosen with the cross, the CMSA procedure, the cross model selection and averaging procedure. So everything will be automatic. So you don't have to do. You can try many values and then it will just pick the best one based on the validation sets. Okay. So I will finish with some application of some ongoing work that something I'm working on right now. I'm trying to build a polygenic score for 240 phenotypes within the UK Biobank. So the UK Biobank is like this large study of 500,000 people, where you have like genetic data and phenotypic data. So I just show that. So I'm using like more than 400,000 people as training set, and I'm using people of European ancestry. I will tell you why I'm talking about ancestry here, because it's important in genetics. But more than 400,000 people, and 1 million, more than 1 million variants. So the variable more than 1 million variable that are of good quality. So you end up with a matrix that is like more than 400,000 times more than 1 million, which is very, very large. But we can still do it. So the phenotypic data. So as I said, every individual you have access to genetic data, but you have also access to many phenotypic data. And I could, for example, get information like for 240 phenotypes, which is like half continuous and half binary. So the continuous one would be like things like body measurements, like height, BMI, and also like things like blood biochemistry, like the level of vitamin D that you have in your blood and so on. And the binary phenotype would be like mostly disease, like if you are diagnosed with breast cancer, skin cancer, or diabetes, heart disease, and so on. I've just fitted like penalized linear regression from my package BigStatR for the continuous, and then penalized logistic regression for the binary ones. And if we look at the results, so I'm just showing here the best 15 results. So this is the third column is the area under the ROC curve with the score using only the genetic variants. And then on the right is the score using all genetic variants plus all the covariates like sex, age, and the principal components. And the second column is like the number of cases I have in the data. So you can see like things like do you have red hair is very easy to predict, and it's also mostly very irritable because you get some very good prediction. I talked before about like things like celiac disease, like autoimmune disease also are quite easy to predict, quite good prediction for them. And yes, yeah, so basically there are some traits or diseases that can be predicted even if you don't have many cases, because, for example, for autoimmune disease, you have like some large effects in chromosome 6, for example. But there are also some diseases and traits where it's not the case, and then having only 1,000 cases is not enough to predict anything. Or as I said before, you can have like diseases that are not irritable at all, or just a bit, and then it's also very hard to predict anything. So here it's just the best prediction that I can get. And if we look now at the continuous phenotype, so the best one, it would be height. So I'm using here the partial correlation. So it's the correlation between the polygenic score, so the score using only the genetic variants, the association, like the correlation with the phenotypes, once you have adjusted for like the covariates like sex, age, and so on. The sample size is not really the sample size of the training set, but the sample size in the whole data. So you need to scale this a bit down. But you can see that you have like huge sample size, and then even if height, for example, is a very polygenic trait, meaning that there are many variants associated with the disease, but they all have a very small effect. But that does not really matter because the sample size is so large that you can still pick up many of these small effects and estimated them well because of the sample size. And then this partial correlation, if you square it, then you would get something like 40% of variance explained, which is quite good. And a last thing I think that is very important to talk about is another limitation of polygenic score. It's when you try to predict in different ancestry. So let's say, so here I'm using Europeans to train the model using penalized regression. And then if I evaluate this model in other ancestries like Asians or African, then the prediction is getting much worse, especially for Africans. So if you look at so this is the partial correlation again, European versus South Asians, and then East Asians, and then Africans. And if you look at the slope, so each point is a trait, right? A phenotype. If you look at the slope and square it, then you can see, for example, the Africans, the slope is like 19%. So it just means that the prediction in Africans is like much worse than what you would get in Europeans. So you have to. There are still a lot of work to do to solve this problem of bad prediction in other ancestries. And so last thing, because I mean I've fitted all these models for 240 traits, but for each of them I fitted many, because you know that there are this kind of cross-validation where you fit like 10 models for each set of hyperparameters. So for each phenotype, I fit a lot of models. So I could just look at all the models that I've fitted and compare the time it took and compare with the number of non-zero variable. So variables with a non-zero effect at the end. And basically what you see, because the time is in a square root scale, you can see that the running time is quadratic with the number of non-zero variables. So for the most polygenic traits, so for example, height, it can take a lot of time, like 50 hours to train the model, but it's like more than 400,000 individuals time more than 1 million variables, so it's like a lot. But if you have like traits that are not that polygenic, I mean, not very polygenic, then you can end up maybe with like 10,000 non-zero variable, which is already a lot. But then the time is only 1 hour, so it's quite fast. Okay, so to conclude, so using the R package BigStatR, you can fit penalized regression on hundreds of gigabytes of data. So the UKB bank is even larger than that. And what I want to say also is that this package is not specific to genetic data at all. It's just some matrix formats stored on disk. So if you have any other data that is in matrix format, then you can use all the functions that are from this package. So I've used it, for example, to build Polygenic score for 240 traits in the huge UKB bank data. And also, I just want to say that more work is needed, especially for the improving the Polygenic score in other ancestries. And if you want to read more about this, so there is this paper describing the R packages, BigStatR and BigSnipR. So BigStatR, nothing to do with genetic, it's only a stats model on large data. And the BigSnipR is like something on top that is specific to genetic data. And then there is this paper specifically describing the penalized regression implementation that I showed today with some application to genetic data. And there is also a tutorial on the package website, for example, to better illustrate some parameters of the function and so on. And yeah, so the presentation here is available online if you want to look at it, and that's all. Thanks. And if you have some questions, I will be happy to answer them now.
Thanks very much, Florian, for this excellent talk. Yeah, as you said, if anyone has any question, please, you can just unmute your microphone and just ask.
There are some questions in the chat already.
Okay.
Hi.
I can just read them. If anyone else can raise their hand, I can invite them. So just one moment, my chat is now. Okay, so let's see, there are many questions. Oh, sorry, because my computer is being lazy at the moment. One moment. Here, okay. So Daniel Stoll is asking, Florian, did you compare elastic net polygenic risk scores with the standard GWAS approach, with the standard PRS or the standard GWAS approach?
So in you mean some polygenic score based on some stats?
Yeah, what do you mean, Daniel? So analyzing SNPs one by one, or using polygenic risk score, the traditional one, using p-values as a threshold?
Yeah, to see if, I just want to know if the new method, the method you use, is better than the standard approach. So if you compared all these C values that you improve something. And
yeah, so in the paper describing this penalized regression and with some application to genetic data, I compared to the standard clumping and thresholding that is used in genetics, right? And what we've seen is that so for example for celiac disease, it's there, right? You can get the AUC for the C plus T model that is lower than what you get with the penalized logistic regression. So what we've seen is that when the sample size is larger, or when there are some effects that are correlated, for example, for celiac disease, you have strong effects in the HL region, which has like strong correlation between the variants. So in this case, it makes a lot of sense to use penalized regression instead of C plus T, because it better handle the correlation between the variants.
Okay, thank you. There are more questions in the chat. So Mariam Shoai, sorry if I'm mispronouncing the name. So he's asking, could this inferior prediction in non-European population be corrected for using LDU maps?
LDU max?
I guess it's linkage disequilibrium. You maybe, Mariam, can clarify.
Yes, exactly. The maps based on how different SNPs relate to each other in different populations. It's a paper published by Nicholas, I forgot his second name, Manti something, I can't remember the second name, my apologies. But it was published Manitius, that's the one. And it was published quite recently, where they tried to link SNPs in different populations together, and therefore increase so things that were previously thought not to be hits in, for example, African populations for type 2 diabetes are now turning out to be when you actually try to link the SNPs together.
Yeah, I don't know about this new work. If you can send it to me by email, it would be really nice. So something that I tried is to look at, for example, you can I don't know, you can have get the FST, the fixation index for every SNP, to look at like variants that are different in other populations. So I've tried to use that to penalize differently the variants in the penalized regression. So for example, if you have like strong differences in allele frequencies, for example, between populations, then I would penalize more this variant. So to keep basically only the variants that are the same in all the populations. I tried that and it didn't really work. I mean, it was basically the same. So I was kind of disappointed, but yeah, I don't know about the work you're talking about. I should read about it.
Yeah, sure, I'll send in here, but I was just wondering if you knew what could be the explanation for this inferior prediction.
The explanation, I think most of it is because basically the variant, the genetic variant that you have in your data usually are not what we call the causal variants, meaning the true variant with the effects. And in fact, it's just some tagging variants, so some variants that are correlated with the causal variant. And because this LD pattern, these correlations between variants are different between one population to another, then you are not tagging the causal variant in the same way in the training set that in the test sets. And I think it's the main reason why the prediction is much worse in other ancestries.
Okay, thank you.
Hi, it's Cedric. As it seems that Raquel is frozen there. Are you there, Raquel?
Yes. Sorry, I'm here now. Can you hear me?
Yes, you're fine.
Sorry
You're
about
fine.
that. Yes, yes, you're right. Then I don't know why I have bad network quality at the moment. I'm just turning off my camera just in case. And I'm going to read the next question. This is by Jody Lord. Thank you, Jody. There are two questions. The first one is, Florian, how well does it deal with linkage disequilibrium, especially if only using the L1 penalty? Because isn't LASSO fairly non-discriminant when dealing with such a high correlation amongst SNPs?
Yes, so basically, when you have like two variants that are basically exactly the same, like the correlation of 1, then the lasso will pick one of them randomly, or I don't know, depending on the algorithm, and not the other. And something like age regression instead would pick both and then give them half of the weight for both. So usually age regression is quite better in when you correlate variables, and then lasso is not very stable. But what I've seen is that if you have enough sample size, lasso is always the best, and you can always use elastic net localization, and usually it has the benefits of both lasso and ridge. So I think like for very what I would recommend is like for very large sample size, you can use lasso. It's okay. And if you have like a bit smaller sample size, then you can try some of the elastic net with some of the alpha that are not equal to 1, but smaller than this.
Okay, there is another question from Jody as well. So she's reminding us that there has been developed very recently a package by Trevor Hasty, from the team. We know him from the team from Robtif Shirani as well, from Stanford. And so Jody is asking if there's a big difference between this package that seems to be an extension of GLMNet and your package, or how they compare. Yeah.
And the algorithm, and so it's very, very similar.
Mm-hmm.
Yeah, it's very similar. Their package is using Plink2, the Pgen format, I think. So it's very specific to genetic data. In comparison, my package is really just any matrix format. So you can use it as well as in other fields, like for example for other omics data and so on. So I would say that mine is more general.
Another question. So sorry, I mispronounced the name, but Anubhav Kafel. What was the rationale behind reducing map SNPs? Would your estimates have remained consistent had you randomly selected around the same number of SNPs from the UK Biobank data?
So usually we use the HapMap3 variants because there have been undertaken some quality control. So usually there are good variants that are also well inputted in many studies. So it means that you can reliably use these variants and then predict in some other data set, and that they should be also quite reliable there. So this is why we use the HapMap3 variants. But yeah, so I think if you pick 1 million variants randomly on the genome, you would get some prediction that is worse, at least if you take your score and predict in a completely other study.
Okay, thank you, Florian.
Hi, Florian. I had a question. I'm Cedric. I mean, if you could go back to slide 15.
Yes. Yes.
So I think so here. So what is going on? Because you're saying that you can sort of switch. You can omit exploring the full range of the lambdas, but what is the rationale for stopping where you stop? And when you say that your package is using the same sort of algorithm that Hasty is using in SPNet, is this what you're referring to? They've got a similar stopping rule that you have.
Yes, I mean, we are using the same algorithm. We are using the same. So there are underlying. There are some strong rules that we're using. So it's some rules that enables you to discard some variables. So you don't have to fit the algorithm. You have to fit it only in a subset of the data because of the strong rules. So this is strong rules that are developed in 2012 or 13, I think. So we are really using some similar stuff. The only difference is that I was published before and they are not published yet.
Okay, but in terms of the specifics there, so the stopping rule is based on the idea that at that point, when you stop, you can somehow anticipate that the rest of the exploration is going to be wasteful. How can you be sure? How can you be sure that the rest of the exploration is not going to detect further variables?
So you're not sure, but usually it's this loss function are very smooth, and this figure here is based on the celiac disease example that I presented before.
Mm-hmm.
And basically when you have like even a larger sample size, you expect this prediction on the validation to be even smoother. So you can. So what I recommend, for example, in the tutorial is that, for example, if you have like QKB bank data, you can stop after 2 iterations when you have found the minimum, and it's okay because the data is so large and this curve is so smooth that you are practically sure that the model is just getting worse and worse on the validation data.
But smooth, I don't really see why smooth would have an effect. I mean, it has to be monotonic.
Yes.
I think.
No,
more than smooth. I mean,
monotonic.
smooth. I mean, the smoothness is just. It's just going to be differentiable. I don't really see how. But monotonic, certainly. You need to ensure that we've reached the bottom essentially of the curve.
Yeah, well, when I said smooth, I was meaning also monotonic before and monotonic after in the other direction. Yeah.
Okay, that's good. Okay, thanks a lot, Florian. Thank you.
Thanks, Edri, for the question. Is there any other question for Florian? Okay, so Richard really is asking now. So thanks, Richard. And so nice talks, impressive that you can develop prediction models in such P higher than N settings. How about stability? So I worry about calibration of such models in new data. In particular, penalization methods like Lasso are known to work well on average, but often fail in the particular data set we want to develop a model in. See, for example, and he's sharing a link to a publication. I'd rather we work in situations where overfitting is minimal and can be precisely adjusted for.
I'm not sure I got all the question, but the question is
about stability and that he's worried about calibration of such models in new data. In particular, yeah, you can see it in the chat if you want.
I don't know where the chat is.
Sorry. So on the top, on the right
I'm full
left
screen.
hand of the hand, you will see like the bubble of the chat on Teams.
I think I don't see anything when I'm presenting, sharing my.
No worries. So it's like that. Richard is saying maybe Richard can tell the question himself, or.
But the question about stability. So there are two kinds of stabilities.
Yes. calibration of such models in new data, especially because of lasso is known to work well on average, but fail in particular data sets.
So the question about stability, so are you talking about stability of the selection of variants or stability of the prediction?
Hi, it's Richard.
Thanks, Richard.
Yeah, sorry. Thanks for trying to interpret my comment. Yeah, really nice talk. And yeah, it's just really interesting, fascinating to see models being developed in P bigger than N settings. I know it's very popular, but I develop a lot of models in N greater than P settings and still have lots of problems of stability. So I mean stability in terms of different variables being selected to come into the model, but particularly when you apply the model that's being developed, you often get miscalibration in different data, even after you've used penalization methods. So my question really is in terms of whether these models do truly calibrate well in new data. So in the link I've posted in the comments, I posted a link to a paper by Ben van Kalster and colleagues. And they just show that the penalization methods like lasso, they work really, really well on average. So across all models that are developed using lasso, on average, the penalization does work well and adjusts for overfitting. But in your one data set that you or me are developing a model in, penalization not necessarily guarantee any better performance in that particular situation. So it's just a question about, have you looked at, maybe through simulation, whether these methods are stable in new data from the same population?
Yeah, usually they are very stable, and the calibration is quite good. But I think you have a different scenario that I have, meaning the large N, small p. I think it's maybe behaving very differently that in our scenario where we have like lots of variables and now also maybe lots of samples. So I'm not sure we can compare how penalized regression are working on the settings like of genetic data, for example, and in some other settings where you don't have many variables.
Yeah, it could well be that in your setting things are so highly correlated that you can maybe work slightly better, but that'd be interesting. Just anyway, it's the link to the paper is in the comments.
But I've looked a bit about the stability of the variants selected, and I have to say that the stability of selection in lasso for genetic data is very bad, meaning that you can get completely different set of variants in the end, but the prediction would be about the same because these variants are so correlated between one another.
That's interesting. Thank you.
Thanks very much, Richard. Thanks very much, Florian. And well, we are over 5, so I think that this was the last question. So thanks very much for Florian for this excellent talk. We can just clap our hands a little bit, even if we cannot see it. Thank you. Thank you.
Yeah, if you have more questions or want to share like some paper with me, please do it by email or Twitter. It would be because I don't see the chat at all. Yeah, so
I will put your email in the chat as well, Florian, if you are happy with it, so that people can email you if they have any other questions.
Yeah, and okay, the Twitter I just
you have it here. Excellent. Okay, thanks very much, and thanks everyone.